A typical engineering design process starts with a set of design requirements coming from the customers. Designers and engineers explore the existing database to select a suitable baseline design. They then go through an iterative process, making slight changes to the baseline design and evaluating its performance until it satisfies the new design requirements. However, this process is extensively time-consuming and highly depends on the expertise of the designers. The only industry-standard way to automate this design process is through shape optimization. Let me give you a brief overview of what a typical shape optimization looks like. Consider that we have a baseline design, in this case a shape, and the objective is to reduce its drag or resistance. We will first select a baseline design and parameterize it with a set of design parameters to seamlessly achieve different design variations. This parameterization results in a design space which will be connected with a physical model that evaluates design performance, and then we will connect it with an optimizer which will explore the design space for an optimal designs. However, the ability of this approach to produce an innovative design is highly dependent on the parameterization and the resulting design space. The ability of the design space to produce rich and valid design alternatives is a crucial component of the shape optimization pipeline, as it determines the quality and the innovativeness of the solution produced. The ability of a design space to generate a diverse and a valid set of design alternatives is a vital component of shape optimization pipeline. This ability directly influences the quality and the innovativeness of the solutions produced. The design space, stemming from the parametric models that are pre-coded to parameterize the key feature of the baseline design, often possesses several limitations. We've recently seen how generative models have overcome these limitations by providing rich design spaces that allow for the creation of innovative shapes. Typically used generative models in various fields include generative adversarial networks, variational autoencoders, diffusion models, and transformers. Generative adversarial networks, in short GANs, use a game theoretic approach with two components, a generator and discriminator. The generator aims to produce realistic data while the discriminator tries to distinguish between the real and the generated data. The two components are trained simultaneously, competing each other. Whereas the diffusion model excels in capturing sequential dependencies, and at the core of the transformer is the attention mechanism which allows the model to focus on different parts of the input sequence when processing it. The design spaces resulting from these models are not only low-dimensional to expedite the shape optimization, but if properly trained can also produce novel and valid design alternatives beyond the spectrum of the training dataset. Generative design spaces promise unparalleled design possibilities. However, how they fit into real design scenarios remains a question. It is vital to know how to optimally use these spaces without overwhelming designers and still speeding up the design process. We must explore if existing techniques, which are mainly developed to explore narrow design spaces coming from the traditional parametric models, can be applied to the vast realm of generative models present. Furthermore, it is crucial to see if designers are open to adopting these generative spaces and how they might harness their full potential in unique and challenging design scenarios. To achieve this understanding, the present work investigates the most efficient ways of exploring generative design spaces. We first construct a complex design problem, such as ship hull design, where parametric modeling plays a vital role. We then create generative design spaces for the hull design, or the ship design in this case, by training a custom GAN model, ship hull GAN, on a large dataset of various ship types. We then develop 3 design exploration modes with varying degrees of autonomy or user involvement. The random exploration mode is a typical preliminary design phase where designers independently explore the design space based on their intuition and expertise while considering performance. In the semi-automated exploration mode, both designer and optimizer collaborate to guide the design exploration towards user-centered and optimized areas of design space. The automated exploration mode is the standard design exploration scenario where the optimizer is the primary driver and the design space exploration occurs while taking performance into account. With these exploration modes, we aim to conduct a user study to understand how designers or naval architects, because our problem in this case is ship, perceive different mode of design exploration in quest of generating novel design solutions from generative design spaces. This is our main focus. To understand to what extent in each exploration mode is effective in achieving diverse, novel, and better performing design, and which factors are the key consideration for design exploration. Either is it the performance or either is the design appearance. As we all know, one of the primary challenge in engineering design is the availability of the data. This is particularly true in marine sector. First, there are few ships than say cars or planes. Second, the maritime community tends to be more conservative. Many ship manufacturers are hesitant to share their design data. Given our need to train our model on realistic and physically validated design, relying on open design libraries was not feasible. Therefore, we begin by selecting 17 different types of ships, including tankers, containers, bulk carriers, tugboats, and crew vessels. These models are either physically exist or they are widely recognized for the validation purposes in the main maritime community. We then introduced systematic variations by parameterizing each design, and this process resulted in approximately 50,000 design data points that we then use to train our ship GAN model. Once the training is completed, the generator component of the ship hull GAN model is used as a generic parametric model. This provides a rich 20-dimensional generative design space which facilitates user in exploring design variations for a wide variety of ship hulls. The resulting design from these variations include both traditional and conventional hull form, which we can see in these design variations. For the first three mode of exploration, a simple optimization problem is formulated. Aim of this problem is to explore this 20-dimensional generative subspace resulting from the ship hull GAN model to create a container ship with a load carrying capacity of 3,600 TEU while minimizing its wave-making resistance or drag. Random exploration mode is based on typical random design exploration approach where the user manually explores the design space for novel and better performing design based on their intuition. To simply explore the 20-dimensional explorers, we first sampled 30,000 designs from the generative design space, ensuring they meet all the previously optimization constraints. For better design exploration, these are then projected on two-dimensional design spaces as it is easier to navigate a low-dimensional design space. During the design exploration, user can access the performance value of each design for a balance of performance and novelty. We don't display performance in real time to prevent bias towards physically based designs only. So once a user finds an intriguing design, they can click on this performance evaluation button and the user can then see the performance. Users are given 30,000 designs and asked to pick 5. The goal is to identify the designs that are both novel and optimized. The novelty of the design is based on how design is unique and if or not designer have previously worked on design something similar to this design. Thus the aim is the design that is both distinct. Distinct means it has different features and has the minimum performance. During this exploration mode, user and optimizers work together to navigate the generative design space, aiming for novel and optimized designs informed by user's intuition and performance metrics. We start by presenting user with end designs and their performance values. The user then select designs based on form and physics. This step facilitates design comparison and informed decisions. After choosing a hull form, the design space is refined. This refined space is inputted to the optimizer, producing new end design for the subsequent iterations. Throughout this process, each batch of design should echo users' prior choices, leading to a final preferred design. This is done by continuously refining the design space, considering user preferences. We apply the space shrinking techniques that pinpoints and exclude non-potential regions, continuously narrow down the design space towards user-preferred designs and away from the less preferred design ones. In these exploration modes, optimization explores the generative design space solely based on the performance metric. This direction aids in potentially reaching the global optima, adhering to certain design constraints and minimizing a specific weight function. This function consists of two elements. The first is performance and second is introduced to incorporate your user preference. We recruited 20 participants for our study in adherence to the protocol set by both University of California's Institutional Review Board and University of Strathclyde's ethical panel. These participants were all final year undergraduate students with a background in naval architecture, and all the participants indicated that they had 3 to 4 years of experience in ship design. The average age of the participants were 25, and the gender distribution between male and female was 30 and 70%. By looking at both design histories and final results, we can get a clear idea of how effective an exploration method is. In our study, the design history covers overall time spent by the participants in each exploration mode. time spent on each design, number of the design explored in each mode of exploration, performance of all the explored and the preferred designs, or the indicators to select the design. Either it was performance or it was based on its design features. This figure displays how much time participant took in each exploration mode. Notably, among the three exploration modes, the participant took the shortened time in the random exploration mode. The time difference between the semi-automated and the fully automated exploration mode was minor. On average, participants finished the random exploration mode in 5 minutes, semi-automated exploration mode in 11 minutes, and then fully automated exploration mode in 10 minutes. Even though we thought participants would need more time in the random exploration mode to find a unique and top-performing design, they actually explored about 1,630 designs in shorter framework than compared to the other exploration modes. This figure gives insight in the average time participants spent on each design. What stands out is that those who explored fewer designs actually spend more time analyzing each design. The time measured for each design is basically the duration when they start viewing one design until when they shifted to another. When we look at the distribution of the total number of designs explored during each exploration mode, these results indicated that within semi-automated exploration modes, participants were able to quickly scan the generative design space with the least number of designs, taking approximately the same time in the automated exploration mode, which has the highest level of design exploration autonomy. It is interesting to note that diversity of the preferred design in random exploration mode is significantly higher compared to the other modes. Automated exploration mode has significantly lower diversity, indicating that designs were highly influenced by the performance without much focusing on the diversity, even when the objective function indicated a term to induce human preference for novelty. It is noteworthy that design resulting from semi-automated exploration mode on average perform better compared to automated exploration mode, which is highly performance driven. However, design resulting from random exploration mode are diverse but do not have good performance. In conclusion, participants find better performing and diverse design with semi-automated exploration mode while exploring fewer designs compared to the automated and the random exploration mode. The result of this study showed that the highest design diversity occurred during the random exploration mode, followed by the semi-automated and the fully automated design exploration mode, whereas the better performing designs were found in fully automated exploration mode and semi-automated exploration mode. However, semi-automated exploration mode outperformed both random and fully automated mode in terms of exploring designs that have a significantly higher trade-off between novelty and the performance. The results of this study also showed that the participants were very good in exploring novel designs with different features, when the performance wasn't taken into account. However, when the performance was brought into the exploration mode, they immediately tend to select the design solely based on the performance and neglecting the design novelty or the designs with distinct features.